Hello everyone, welcome to Dakshana E classroom program. So in the last lecture we talked about aging or dating, that is basically application or one of the application of radioactivity. So in that we discussed about carbon dating, right? So we learned that how with the help of carbon dating we can find age of some like old things like living arm, like some plants, dead bodies, skeleton, something like that. And I told you that when the age of something like which we are interested to find is in some, like let's say 10,000 year, 20,000, 50,000 year old, there it's good to use carbon dating. If the age of something which we are interested to know is in lakhs and millions of year old, in that case your carbon dating doesn't work properly. The reason for that, by that time the carbon 14 elements decayed almost completely, so you will not be able to find the carbon 14 elements or atoms present in the old sample effectively, and there your calculation will get disturbed. So in such case we have another important like aging method, and that is called uranium aging or uranium dating. Let me tell you how it is there, like how it work and how we can calculate age of some sample with the help of uranium dating. So in uranium also, actually there are like radioactive elements, radioactive isotope. So there is one isotope of uranium which is normally present in some rocks, and is it uranium, that is uranium 235. So what happened actually 235? So in this case uranium 235 92, it get decay and finally converted into lead 82 207, and this is the stable nuclei, right? So this is the process happening inside the rock. Now what we do actually here, so we take some sample of the rock, is it? So take some sample. I'm explaining you here the method how we can approach, how we can calculate the age of that rock or something which we are interested to know. So we take some sample of that rock, is it, or anything which we are interested to know. So let's say I took one sample of some rock and it has, we will calculate the amount, is it, of uranium 235 present and lead 207 present in that sample. So let a gram of uranium 235 is present in that sample and some b gram of lead 207 is present in that sample. So if a gram uranium 235, b gram uranium are like lead 207, I can get the number of atoms. So you can write number of atoms of uranium 235, this will be A divided by 235 molar mass, is it? You can write number of atoms of uranium 235 in the sample. Similarly B divided by 207 will be number of lead 207. So this is the decay process that happened in the rock. We took one sample of the rock. In that sample we calculated the how much uranium 235 is present and how much lead 207 is present. So let's say after calculating and finding and doing that calculation, we got that a gram of uranium 235 is present and b gram of lead 207 is present. By simply dividing their molar masses, we can get the number of atoms, number of elements of uranium 235 and number of atoms of lead 207 present. So up to now we just did this calculation. Now how we get the age exactly? So here we use one assumption. The assumption here is that we assume that initially at the time of formation of rock only uranium 235 was present. Means right now whatever the lead is present in the sample, we assume that all the lead actually has been converted from uranium, or all the lead present in the sample is the product of uranium 235 decay. This assumption we consider in finding the uranium dating or finding the age with the help of uranium dating. So the assumption is that it is assumed that at the time of formation of rock only uranium 235 was present, no lead 207 atom. Means all the lead 207 present now in the sample is the result of decay of uranium 235. What it implies, that should be like it's important point here, actually you should understand this. So I mean here actually that now in the current sample we are taking from the rock, it has these many number of uranium 235 atoms and these many number of lead 207 atom. So what I can say that the initially number of atoms of uranium 235 present was how many, this plus this number of atoms. So if I add, because single uranium 235 converted and that result in only single atom of lead. So means if I will say, let's say just for simple example, let's say I'm saying 100 atoms of uranium 235 is present now and 50 is lead. So means all these 50 atoms are coming from where? Uranium 235. So initially what I can say, initially at the time of formation of the rock, how many atoms of uranium 235 was present, and that you can write simply 100 and plus 50 has been decayed. So the total number of uranium 235 atom presents at the time of formation of the rock was 150. So now we have number of atom of radioactive element 235 at the formation of rock and number of atoms of uranium 235 present now. And when we have these two things, we know the relation from the radioactivity decay law, that n equal to n naught e raised to power minus lambda t. Again by using that, and we can simply substitute in the formula and we can get the time, that how much time it has taken to decay uranium like at 235 atom or 150 uranium 235 atom to 50, or 50 decayed or means 100 left. So that time we can calculate, and that time will be the actual age of rock. So this is the method, this is the approach how uranium dating work. Let me show you here the calculation part for uranium dating. Conceptually, fundamentally how things are working, that should be clear to you now. Simple things are there. This is the process happening in the rock. We took one sample, get the mass of uranium 235 present and lead 207 present, because this is getting converted into lead 207. So by like simply dividing their molar masses, we got the number of atoms of uranium 235, number of atom of uranium 207. Then we have here one assumption, and assumption is that whatever the lead right now present in the rock is the product of uranium 235 decay. Means uranium 235 has decayed, only that decayed part is converted into lead. So now with this assumption I can write number of uranium 235 atoms present in the rock at the time of formation of rock. So this I can write, let me write it an old, is it? This will be equal to what? This is A divided by 235 plus B divided by 207. So this is the N naught present at the time of formation. How many uranium atoms are present in the right now? Is it number of atoms of uranium 235 present in the current sample. So this you can write, let me write, it's N, and that is equal to what? Simply A divided by 235 atoms. And now we have the relation between these two things. So let me just erase this part here. So by using the law of radioactivity and the relation, I can write I have the relation between these two, that comes N is equal to N naught e raised to power minus lambda T. Here you will require T half. So T half actually for uranium 235, it's 9.5 into it's actually 4.5 into 10 to the power 9 years. This is the half-life of uranium 235. So we got this, and from half-life we can get lambda is equal to ln2 divided by T half. This relation you already familiar. Now we have here N, we have N naught, we have everything, so we can get that value of T, and simply T is coming out to be, this is, if I just solve it, then it's 1 by lambda ln N naught divided by N, and this you can rearrange it, and this is T half divided by ln 2 multiplied by ln N naught divided by N. So now once you have this number of atoms present in the number of atoms of uranium 235 present at the time of formation of the rock, number of atoms of uranium 235 present in the same sample. Now this ln2 simple from this lambda value, substitute the values here and do the calculation part. This time is the age of that rock, so the time T is the age of that rock. So I think this is the process, this is the method, the strategy, like the approach to use uranium dating for finding the age of any rock. So that should be clear why and how things are working here. You should understand that point. Let me tell you some application of this part also, how we can use uranium dating for finding the age of some very old rocks. Is it? Okay, let's see here one application of uranium dating. Before that, I want to mention one more point here. Actually, I use the uranium 235 radioactive element here. It's not necessary that always uranium 235 will be used. Uranium 238 and other can also be used. So just same way here in this problem we are given in an ore containing uranium, the ratio of number of atoms of uranium 238 and lead 206, because actually uranium 238 finally get converted into lead 206, right? So here this ratio is present in the ore right now when it is measured. So number of atoms of uranium and lead, it's 3 and that is equal to 3 by 1. Is it? Calculate the age of the ore here, assuming that all lead present is the final stable product of decay of uranium 238. So this assumption I told you already, and here it's even mentioning in the problem that assume that all the lead present is formed because of the decay of uranium atom. So T half is given 4.5 into 10 to the power 9 years. Let's just do the calculation and get the age of this ore or a rock. Is it? So exactly same manner here. First thing is number of atoms of uranium 238 divided by lead 206 this is 3 by 1. What it mean actually here? This means if I write here, let's say number of atoms of uranium is 3. In that case, number of atoms of lead is 1. Is it? So you can write here, that means if number of atoms of uranium 238, let's say it's 3x, then number of atoms of lead 206 will be what? X. So I can write at the time of formation, total number of uranium 238 present, what is equal to, this is 3x plus x, that is equal to 4x. So we got actually, this is what? N naught, and n is equal to what? 3x. Right now number of atoms present is 3x. Then we can use this relation, T is equal to T half divided by ln2 multiplied by ln, this is n naught divided by n, right? And this T half 4.5 10 to the power 9 multiplied by, this is ln 4 by 3, x gets cancelled, divided by ln 2. This log we can just simplify it with the help of calculator, or either you can remember the value of ln 3, ln 4, ln 2. With the help of that you can use it normally, like manually, without calculation also, calculator also you can calculate. So this, after solving, it comes out exactly 1.867 into 10 to the power 9 years. So this is the age of that rock. So this is the age of that rock. This is also actually important topic, especially in IIT mains. Sometimes problems are asked based on this. And the approach here, you can see it's easy, actually it's not difficult. Yes, problem you need to try a lot so that you are feeling good, confident about this topic. So this is all about the aging or dating method by the help of basically, or one of the application of radioactivity. There we use only two, that is carbon dating and uranium dating. So let's continue from here onward, then the next part. Okay, so next we are going to talk about is artificial radioactivity, and there we will talk about nuclear fission and nuclear fusion. So before that, we have all discussed that what is exactly radioactivity and many more things about it, stable nuclei, unstable nuclei, decay and all that. Now here what is happening actually, and I told you in the beginning, as world is expanding, so there is a growing demand of energy, and all the available resources they are all not able to fulfill, and we need to search for something like even good source of energy. And one of the example is that nuclear fission, or energy from nuclear like fission, fusion. On Earth, nuclear fusion is not yet possible actually in the laboratory. I will tell you why. And yes, there is one news recently, actually just few like days back, around in January, Germany or France somewhere, like scientists from all over the world, they are like working on producing or manufacturing a nuclear reactor which will work based on nuclear fusion process. Right now there are almost like in every country nuclear like not in every, many countries, nuclear fission process, fission like technology is there. Even in India also there, when we are using it for harnessing energy that like is helping in fulfilling our growing demand of energy. So I will like today tell you exactly what is that. And before that, you know, already here we discussed the binding energy per nucleon and versus atomic number. So what are these nuclear fission and fusion? I'm just telling you in short. So we discussed, it was something like this, the graph of binding energy per nucleon. So binding energy per nucleon, this here for atomic weight of 56, that is iron, it's around 8.8 MeV binding energy per nucleon. As we go beyond 200, then it decreases, and here if we have uranium, then the binding energy of uranium is smaller, binding energy per nucleon. And here if we talk about hydrogen, deuterium and tritium 3 1, their binding energy is also very small. So now here we have two possibility actually, binding energy per nucleon. Here I am talking about what happen actually when these heavy nuclei break down, split into lighter nuclei of almost like equal weights. In this process you can see the binding energy per nucleon is increasing, and if you are remembering things, then binding energy per nucleon increases, then stability increases, and that means more amount of energy will be released in the process. So when this happen actually, heavy nuclei split down into two comparable size nuclei, this is called nuclear fission. And similarly here, if these lighter nuclei combine and form some heavier nuclei here, that is one of the helium, in this process also you can see the binding energy per nucleon is increasing. So in this process, when these are combining and forming a heavier nuclei, here binding energy per nucleon increases, so a large amount of energy is released in this process, and we call this is nuclear fusion. This predominantly happen in like sun. Whatever the process is taking place on the sun is this nuclear fusion, and because of that you can imagine how much amount of energy is produced in the sun. So this is also another, and like if we are able to make these processes happen in the laboratory, in that case what will happen, we will be also able to produce large amount of energy, and that energy can be utilized for further applications. So this is just simple explanation for nuclear fission, nuclear fusion. Nuclear fission, heavy nuclei split down into lighter nuclei with the release of large amount of energy and some neutrons. And in nuclear fusion, lighter nuclei fuse together and form heavy nuclei, and in both the processes a large amount of energy is released which can be utilized. So let me first tell you a little bit more detail about nuclear fission. Here these are more of theoretical points, theoretical part, like here exactly that what are things involved. So I will write down those points and then I will explain you directly. So nuclear fission, it is the process of splitting of heavy nuclei into two lighter nuclei or products, is it, lighter product of almost comparable weights with the release of large amount of energy on bombarding with energetic particle. This process is called nuclear fission. It was discovered by scientist Otto Hahn and F. Strassmann, but explained by Neil Bohr and J.A. Wheeler. So these two scientists explained based on the splitting of liquid drop method. So here what happen actually, if we are having some liquid drops and then some energy is given to it, and that is like what sufficient energy, then this liquid drop start vibrating actually with large amount of energy, that result in splitting of that drops into two almost comparable weights, small drops. Exactly same principle happen here also actually. So if we are having, let's say this is uranium nuclei, when it is bombarded with a high energy neutron, is it, you can write here high energy neutron or energetic neutron, then what happen, ultimately energy is supplied to the uranium and it start vibrating actually. So like this, it start vibrating this way. Sometimes it stretches like this, sometimes closer, like this. So in this way it start vibrating, and that ultimately leads to the splitting of, like, because here what is happening, protons are there, and when they increases some separation here, some proton density and proton density, that they even push it further, and that result in further splitting actually. Like this, split it, and it increases even the separation more. And finally what happened, it break down into two lighter nuclei. This is, let's say, X and Y. So these are fission products with the release of neutrons, neutron. So this is fast neutron. These three fast neutrons are released, and this is how actually nuclear fission takes place. So this, like, is simply here with the, like, nuclear fission, these fast neutrons are produced, and with large amount of energy is also released. Let me write next points. So one of the fission reaction of uranium-235 is when uranium-235 bombarded with neutron, it get converted into uranium-236, which is like high energetic, and this start vibrating and further break down into barium and krypton, and with the release of 3 neutrons and some large amount of energy. Here the energy released is about 200 mega electron volt per fission. Around 200, and this 200 mega electron volt energy is like huge, or it's almost 0.8 MeV per nucleon. You know, actually Hiroshima and Nagasaki bomb explosion, there in per nucleon the energy released was 200 mega electron volt, and how much destruction it caused, you know that actually. So this is normal thing, like in nuclear reaction, this is what almost like 200 mega electron volt per nuclear fission of uranium-235 energy is produced, and up something around 0.8 mega electron volt. And here we can definitely write the mass of compound nuclei must be greater than the sum of masses of fragment or product nuclei. Because in this case you can see when mass of compound nuclei will be higher and final mass is decreasing, in that case this mass defect will be resulting in the production of energy, so by Einstein's energy. So we can write this, and for a fission like a reaction we can write also the binding energy per nucleon of compound nuclei. Compound nuclei here means uranium nuclei must be smaller than the fragment nuclei. In that case also stable, like large amount of energy will be released. Few more point about the nuclear fission. Here in the fission of uranium-235, this occur first thing is only with the slow neutrons or thermal neutrons, means the energy of neutron must be in the range of some electron volt, or for thermal neutron it should be like something 0.025 electron volt. But the neutrons released in the fission process of uranium-235, they are fast neutron, they carry an energy of something 2 mega electron volt per neutron. So these neutrons to be used in the chain reaction, to be used for the further initiation of fission of uranium-235, then these need to be slowed down. Yes, we have methods to slow down the neutrons, and they are called moderators. Moderators slow down the neutrons basically. And it is not I wrote one example here there where uranium 235 was breaking down into barium and krypton. It's not always necessary that every time neutron like uranium 235 will be breaking down into barium and krypton. It can break down in some other medium weight or middle weight nuclei also, like it is breaking down into xenon and strontium. It's 140 and 94 with the release of 2 neutron. It can also break down into lanthanum and bromium, weight 148 and 95 with the release of 3 neutron, and many more. So this is about actually nuclear fission process here. Nucleon, one unstable nuclei or heavy nuclei is there. When it is bombarded with the neutron, it gets split into lighter nuclei with the release of fast neutron and large amount of energy. So this is your nuclear fission process. So here we can see actually in each nuclear fission, on an average 2.5 neutrons are produced, and if we are able to use these 2.5 neutrons for the further fission of uranium, in this process you can see neutrons are produced with the release of large amount of energy. Under favorable conditions, these neutrons can cause further fission of other nuclei and producing large number of neutrons further. Thus a chain reaction, is it? Chain of nuclear fission is established, which continue until the whole of the uranium is consumed. So this is one of the example of chain reaction where uranium, and this is like first generation neutron bombarded, it's splitted, or basically fission takes place with the barium and krypton and release of 3 neutrons. Out of these 3 neutrons, maybe 2 neutrons are used for the further fission of uranium, and the fission is taking place and releasing again large number of neutrons. So these are called second generation neutron, third generation neutron, and further these neutrons will be initiating the fission process for another uranium. So you can see here the fission process, it increases very fast. So the chain reaction, number of nuclear fission process increases very fast, and so the energy produced in this increases tremendous in magnitude. This happen actually in case of nuclear bombs. In this situation, if we are able to control the number of neutrons here released, we can't control, but if we are, let's suppose, able to absorb some of these neutrons and we are releasing only same amount of neutrons which are used there, in that case the reaction rate can be controlled, and that is actually used in nuclear reactor. So let me tell you exactly how nuclear reactor work, and how with the help of chain reaction or controlled and sustained chain reaction we are able to produce the continuous supply of energy from nuclear reactor or nuclear energy. Okay, so we saw actually nuclear fission. It is the process we saw in which the heavy nuclei break down into small middle weight nuclei and having higher binding energy per nucleon. In this process, a large amount of energy is released, and the point is here, for the fission to take place we need slow neutrons, is it? And the neutrons which are produced actually in the fission process, they are fast neutrons. So like we saw, that was nuclear fission. Then we saw also chain reaction in which, if by suitable means, favorable conditions creating, we are utilizing those fast neutrons by slowing down for the further fission, then the reaction rate can exponentially grow and can produce a large amount of energy. So now that was nuclear fission and chain reaction that can be sustained from the neutrons emitted from the nuclear fission itself, so we don't have to supply further neutrons. Now only the problem is there in the nuclear chain reaction, it is growing at faster rate, and that result in explosion, and that is what exactly happen in atomic bombs. So if we are able to control the number of neutrons, is it, in that case the chain reaction can be controlled, and this controlled chain reaction is actually used in nuclear reactor to produce large amount of energy. So nuclear reactor, next we are going to talk about, it is a device actually in which nuclear fission can be carried out through sustained and controlled chain reaction. Sustained means which is continuously like proceeding, not stopping in between, and control where we can control the rate slow and fast. We will see, I will tell you how exactly that thing is actually happen in this nuclear reactor. This is the design of nuclear reactor, how it work. I will tell you that it is a source of controlled energy which can be utilized for various purpose. So first thing is here, actually we uses here some fuel elements. Fuel element, basically it is the fissionable material which is used for the fission in the nuclear reactor. The most commonly used fissionable material in the nuclear reactor are uranium-235 and isotope of thorium-232 and some isotopes of polonium, that is polonium-239, polonium-240 and polonium-241. So these are used as fissionable material in this nuclear reactor, and this is called as fissionable material or element rods. So element rods are made of these. So now what is happening here? Initially we initiate the nuclear reaction by providing from the external source is slow neutrons. Now what will happen when this slow neutron is striking and producing, like fission is taking place, large number further neutron will start producing, is it? Those neutron, first thing is need to be slowed down, and that slow down process is done controlled by moderator. So moderator, basically these are let me define it. The work of moderator help in slowing down the neutrons. Moderator, it slow down the fast moving or fast neutrons. The most commonly used moderator, the commonly used moderator is or are graphite and heavy water. Heavy water, D2O. So D2O and graphite are used as moderator. So those fast neutrons collide with these and become slow. So then these slow neutrons can be utilized for further fission process. Next point. So even just we saw in the last topic, that is chain reaction. Even if we are just slowing down the neutrons, first thing is it should be clear now to you that how, like actually with the help of what we are reducing the speed, or we are making like fast neutrons to slow neutrons so that they can be used for the further fission of uranium or fuel rods or fuel for fission material, is it? So now that is done by moderator and commonly used are like graphite and heavy water. Now these like neutrons, slow neutrons, which are being slowed down now, they are also like increasing more, is it? Means in first fission 2.5, I can say on an average 2.5 neutrons are released per nuclear fission. So next process it will be like growing even further and even higher in next process, and that's how exponential growth rate will be there. But we want in the nuclear reactor the reaction to be controlled. It should not grow exponentially. To control that, we have here control rods. These are normally cadmium rods. So control rod, they are made of, these are cadmium rods. They can absorb the neutrons. So cadmium rods used to control the rate of reaction. Here you can write used to control the rate of decay or reaction. How? First thing is the function of cadmium rod is they can absorb neutrons. So now if we want the reaction rate to be controlled, to be slowed down, we insert these cadmium rods further deep down so that mostly neutrons emitted are absorbed by the cadmium rod and they are not participating in the further fission process. So finally that way like less number of neutrons will be participating in the fission and more number will be absorbed, and finally after some time the reaction will come to halt, will be stopped. If we want the reaction to be like increase reaction rate, we will pull these cadmium rods up. In that case, most of the available neutrons will be participating in the fission process, and that way like your reaction will start accelerating. For accelerating, we don't have to do anything from outside, because itself the chain reaction itself by itself it's accelerating chain reaction. If we are inserting the cadmium rods, then we are taking out the neutrons which are responsible for the fission. That way we are controlling the rate of the reaction. So if we want, exactly we can adjust the length so that exactly like if we want sustained or constant rate, in that case the number of neutrons emitted and the excess neutrons will be absorbed by these cadmium rod. We control that. So that way cadmium rods are also called control rod, and these are used to control the rate of reaction by absorption of neutrons. So here we understood this cadmium rod. Now see what is happening. This is actually the core. This complete set is called core of the nuclear reactor. So you can see here nuclear fission is taking place in this core. Moderator are helping in that fission, and cadmium is used to control the rate of the reaction. Overall in this process large amount of energy is produced, and that is produced in the form of heat. So this heat is then need to be carried out so that like this complete system is not melting out, otherwise it will melt and our system will collapse. So for that we have this is coolant actually. So this coolant is in direct contact with the core and it absorb heat from the core and take it outside. So this is coolant coming out, and here this coolant comes in contact with the water and water get evaporated, and this evaporated steam is used to run turbine, which can further used to generate electricity or for generators. So this steam after that cool down and condensed and sent back to here in contact with the coolant, so that it can be reused for the extraction of energy or can be converted back to steam. And then this coolant here coming hot and finally become cool, and it's again going back to nuclear reactor core so that it can again absorb energy and supply outside. So that is how your heat is extracted from the nuclear reactor. So this is the function of coolant. So overall effectively we see this is the actually part which is effectively working as a nuclear reactor. But what happened actually here, sometimes in this nuclear reactor some harmful radiations are emitted. So if any person working inside this region, then that person, if it is exposed to those radiations, it will be a harmful, it can cause cancer and other problems to that person. So if we want like those radiations to not to come out, for that we like create one thick concrete wall, and that is called protective shield. So protective shield it control the harmful radiations coming out from the nuclear core. So in that way the person which are working outside or in this reactor are still safe. So this is how actually we can control the rate of the reaction by cadmium rods. Fast neutron problem, because fast neutron can't initiate the fission of uranium-235, need to be slowed down, that is done by moderator. And in this process overall like rate of reaction is controlled, neutrons are slowed down, fission is continuously taking place, large amount of energy is being produced. This energy need to be extracted so that this core is not getting melted, and that energy extraction is done by coolant. Coolant uses this energy and supply it outside to generate steam, and which steam is used to run the turbine and generate electricity. So that is how your nuclear reactor work. So this way we are able to harness the energy from the nuclear fission process and can be utilized for generating power and for many more purposes. So that is the application, or this is how a nuclear reactor work. So some of the application or uses of nuclear reactor are, first is the main use, that is in generation of electric power. so electric power generator, also to produce radium isotopes, radioactive isotope for their uses in medical, agriculture and other industries, and used in manufacturing of plutonium 239, which is used in atom bombs, to produce neutron beam of high intensity, which is used in the treatment of cancer and other nuclear researches. So these are some of the common application of nuclear reactor which are effectively using the nuclear fission process in the nuclear reactor. So you can say this is application in indirect form, application of nuclear fission. Let's see the last part, and that is nuclear fusion. So in nuclear fusion, basically nuclear fusion, I told just here what is happening, two and more than two lighter nuclei combined to form a heavier nuclei such that the masses of the lighter nuclei combined added is greater than the mass of the lighter nuclei, that result in some mass defect which produces equivalent energy in the process, and that is called nuclear fusion. So here lighter nuclei are combining together to form heavier nuclei, and a large amount of energy is released. This is called nuclear fusion process. Nuclear fusion process mainly happen in the earth or like core of sun. Their energy is produced exactly by nuclear fusion process. To produce the nuclear fission or to make it happen, actually the requirement is normally the pressure should be in the order of 10 to the power 6 atm atmospheric pressure, and the temperature should be in the range of 10 to the power 7 to 10 to the power 8 Kelvin. So now you can see the requirement here, because to fuse the lighter nuclei they must be brought very closer, their nuclei must be brought very closer, and that can happen only when the pressure is too high, that is of the order of 10 to the power 6, and temperature of the order of 10 to the power 8 Kelvin. And another point is here, we don't have any material which can withstand that much amount of pressure at 10 to the power 7 or 8 Kelvin temperature. So that's why we don't have any setup, we can't right up to now produce any system for creating that much high temperature and pressure and to start the nuclear fission process. Yes, recently we saw some news that in some Germany or France there is some nuclear reactor are being manufactured, or it's being tested, which will be working on the nuclear fusion process. So let me tell you a few more things, more point about it, and the reaction which takes place and how the energy is produced in the nuclear fusion. In nuclear fusion, actually, if we compare it with the nuclear fission, the energy produced from same amount of fuel in nuclear fusion is very or much higher than the energy produced by same amount of fuel in nuclear fission. But the only problem here is that it's next to impossible right now. Also I can say it's impossible to design a system which can use the nuclear fusion process for generating or harnessing the power. So this is about nuclear fission. Let me write few points and the equation for it. So in the nuclear fusion, actually here I can write the two or more than two lighter nuclei combine to form a heavy nuclei. The mass of single nucleus thus formed should be less than the masses of the lighter nuclei or sum of the masses of the lighter nuclei. So this difference in mass will result in the release of tremendous amount of energy, and this process we call nuclear fusion. Normally the requirement for the nuclear fusion to take place is the high pressure of the order of 10 to the power 6 atm, you can just imagine, and very high temperature, that is of the order of 10 to the power 7 to 8 Kelvin, right, is required. So the reaction is also called thermonuclear reaction. So like some example of nuclear fission, which is liberating nuclear fission reactions, which are in terms of neutral atoms, we can write it as here proton, hydrogen means we can call it proton also, proton plus proton combining and forming deuterium plus one beta positive and antineutrino, and here deuterium plus hydrogen combined form helium 3 plus gamma, and these two helium atom combine and form helium 4 plus 1 proton, or when 4 protons combine, they are forming 1 helium plus 2 positive particle and 2 gamma radiations, and 26.73 MeV amount of energy is released. And this, you can imagine, just the mass of 4 hydrogen atom, it's like very small, and the energy released is too much large actually. So here proton-proton chain reaction takes place normally in the interior of the sun. So the sun, the way it produces energy is by the nuclear fission process of protons. Now next is, for the same mass of fuel energy produced in nuclear fusion is much larger than the energy produced in nuclear fission. And another thing is, because here the requirement for temperature and pressure, as the requirement for pressure and temperature is too much high, temperature of the order of 10 to the power 7 to 8 Kelvin and pressure of 10 to the power order of 6 atm. So this much is it. So that we have already written here, temp 10 to the power 6 atm pressure and 10 to the power 7 to 10 to the power 8 Kelvin temperature. This is almost next to impossible, because we don't have any substance, any material which can bear this much amount of pressure at this much high temperature. So that's why this reaction up to now it seems almost impossible to carry out in the laboratory, but still scientists are working to contain that plasma by controlling some magnetic field and electric field, and where we are not using any utensil. Actually, the reaction is not carried out in some material core, just like a nuclear fission, nuclear reactor. So work is going on, and this is all about actually nuclear fission process. Yes, there is some few terms which I did not explain. Let me just tell you that. Okay, some of the definition which I just skipped actually in the initial part. So that is isotopes. So what is an isotope? Isotopes means like atoms having same atomic number but different mass number, and they are called isotopes. Atom of element having same atomic number but different mass number are called isotopes. So here atomic number is same, that means in the periodic table they are occupying same space, that means their chemical properties are same. So all isotopes have same chemical properties as they occupy same space in periodic table. Some of the example of isotopes of hydrogen, isotopes of uranium, isotopes of oxygen. There are many isotopes, so these are few of the cases. Next is isobar. Isobar means nuclei which are having same mass number but different atomic number. Same mass number but different atomic number are called isobars. Here you can see the atomic number is different, means they are occupying different space in the periodic table, so that's why their chemical properties will be different. Some of the example of isobars are hydrogen 1, tritium base and helium 2, 3. So and similarly carbon 614 and nitrogen 714. So their mass number are different, like mass number is same but atomic number is different. These are called isobars. The next is isotone. So nuclei having equal number of neutrons. So here atomic number and mass number both will be different for both the elements, but mass number minus atomic number, that means number of neutrons will be same for both the nuclei, and these are called isotones. So some of the example of isotones is beryllium 49 and boron 510, carbon 613 and nitrogen 714. So here you can see the number of neutrons here 5, number of neutrons here 5, number of neutrons here 7, number of neutrons here 7. So these are called isotones. So these are just simple definition which may be used or maybe sometime required in the chapter. So this was all about the nuclear physics part 2. I hope you enjoyed. You try as many as problem from the material, that is Dakshana sheet and question bank. I will give you the homework for each lecture. Follow it properly, go through the lecture notes properly and listen it and practice and be happy. Stay safe. Corona is going on, and let's see you in the next class with a new topic. Thank you so much. Bye.